All right, here we go, you guys. I'm going to share my screen and we are going to learn related rates. This is section 2.4 in your spiral book. Just follow along with me. Okay, let me get this bigger. There we go. Okay, so when we do related rates, this is some steps that you're going to want to take to do it. You will want to draw a figure if necessary, and then choose the variables that you want to pick for each unknown. Okay, this will all make sense when we start an actual problem. So these are the steps that you're going to take. When you do step 2, you're going to write down what is given and what do you need to find. Okay, we're going to have multiple variables, so we're going to have a lot of different derivatives going on, the d and dt symbols. Okay, if a quantity is changing, it's going to be a letter. If it's a constant, it's going to be a number value. Look for secondary relationships between quantities. So what this is saying is if it says the height is twice the size of the radius, then you would want to write it using only one variable instead of the radius and the height. And like I said, we're going to go through all this stuff, okay? So let's just jump into it and look at example 1. Okay, so in example 1, it gives us the first 3 steps are done. So we're going to do the last 2 steps. Okay, so I have dx dt is -6, y is 4, and my equation is xy equals 12. Okay, so what we're going to do is we're going to take the derivative of our equation. So the derivative of xy equals 12 is going to be first. Okay, so when we take the derivative, we have the x times the y. So what do we do when we have an x times the y? We're taking the derivative, it tells you right here, with respect to t. Okay, that says dt. So what that means is when I have an x and a y, then I have to put a prime for each letter. Okay, so I have x times dy dt. Okay, and then I'm adding, because this is product rule, right? So I did first times derivative of the second plus the second, which is y, times derivative of the first. And that equals 0, because the derivative of 12 is 0. Okay, so here I know what y is. Y is 4, so I'm going to put a 4 in place. Okay, so x, can we solve for x using this xy equals 12? What would x be? Give me a second. Okay, we might not need to do it, but this is what they're talking about secondary relationships. So we have like x equals 12 over y. Oh man, that is tiny. I usually try to print these pages out so they're a little bit bigger for you when I have a little bit of notice. And focus a little bit. Okay, so we're going to plug in each of these values, okay? So when y equals 4, I can solve for x, right? Because x equals 12 divided by 4, so x would be 3. Okay, so that's what we have to look at, these secondary relationships right here. Okay, so I have x times dy dt plus y times dx dt equals 0. Okay, so now I'm going to say, I know what x is 3. Dy dt, I don't know. That's what we're solving for. Okay, plus y is 4, and dx dt is -6. All right, so once we have these plugged in, we're just solving for dy dt. So I'm going to add the 24 to the other side. Okay, so we're going to have 3 dy dt equals 24. And then we're going to divide by 3. And we get dy dt equals 8. Okay, so this is a more basic one where you're given an equation, xy equals 12. We're trying to find dy dt. So notice that these are in respect to t, and there's not a t in my equation. So when I take the derivative of either of these variables, I have to have an x prime and a y prime. That's what this is. The dy dt is the same as y prime. Okay, dx dt is the same as x prime. So we're just writing it with the different variables. Okay. All right, so now we are going on and we're going to use a story problem. Okay. So we're going to do this very top one where it talks about the windlass is used to tow a boat to a dock. Okay, so basically what happens is they have this boat that's out on the water, and we are trying to figure out how fast the boat is approaching the dock. Okay, so what we have to do is we have to first figure out what is given. Okay, so I'm going to write given right here. And I look at this and I say, okay, what do I know here? A windlass is used to tow a boat to a dock. The rope is attached to the boat 15 feet below the level of the windlass. And so if this is x and this is z, I could probably call this y, right? So x, y, z. Okay, and so I know what that is. And then it says here, the windlass pulls the boat or the rope in at 30 feet per minute. So I'm pulling this rope and it's getting shorter and shorter, the rope is. Okay, by 30 feet shorter per minute, it wants to know what rate is the boat approaching the dock when there is 25 feet of rope out. Okay, so the rope in the picture right here, so I have windlass and I have a rope. It's attached here and it's going to get smaller and smaller and smaller. So dz dt is negative 30. Okay, I'm doing a negative because the distance is getting shorter. So negative 30 feet per minute. Okay, so I know that. And then it says, what rate is the boat approaching the dock? So I have to look at this and say, here's my dock right here. And x is the distance from the boat to the dock. So I'm looking for this value, but I want the rate of this value. So what I'm searching for is dx dt. That's our question mark. Okay. We know that z is 25 at the moment that I'm looking for. Z is 25. The windlass is 15 feet above the dock, and that distance does not change. Okay. So that's going to be important when I figure out what x is going to be. So I need to use the value they gave me, the 25 for z, the 15 that I know, and I need to solve for x at the exact moment that we're looking for. So the relationship on this triangle, I hope you are all thinking, is the Pythagorean theorem. So x squared plus y squared equals z squared. Okay, so I know that x is what I'm looking for, and I know that y is 15, okay, squared, and that's not going to change. No matter what I do, that's not going to change, okay? So, and then I know that z is the hypotenuse, so it is 25 squared. So using this, I subtract the 15 squared and I take the square root, and I get x is 20, okay? So x is 20 feet So the boat is 20 feet away from the dock at the moment that we're looking for. Okay, so now I have to change this equation into rates, okay? So I have x squared plus 15 squared equals z squared, because I don't know what these are at the moment we're looking for. So I take the derivative of x squared and I get 2x times dx dt, okay? The derivative of 15 squared is 0. The derivative of z squared is 2z dz dt. Okay, so we have these variables. Okay, well, if I have a 2 on here and a 2 on here, can't I cross the 2 off? Because those would cancel out. So now I'm plugging in. I know what x is. X is 20. Dx dt is what I'm searching for. And then we know what z is. It's 25. And I know what dz dt is. It's negative 30. Okay, so using that, we're going to figure out that dx dt is going to be 25 times negative 30 and then divide by this 20. And we end up getting negative 37.5 feet per minute. Okay. So if I have to write a sentence to explain this, what does it mean at negative 37.5 feet per minute for x? So think about this means the rate of change, right? So I'm going to say the boat is approaching, or let's say getting closer. Then we know it's a negative value. Either way, you can say approaching, or you could say the boat is getting closer to the dock at 37.5 feet per minute. Okay, so the boat is getting closer to the dock at 37.5 feet per minute when, okay, so we always have to have and say when we did it, okay? So when there is 25 feet of rope out, okay? So you always identify what the rate is, but this rate will change depending on how many feet of rope is out. So that's why you always have to say when 25 feet of rope is out, okay? All right, let's try another one. A policeman traveling south towards an intersection spots a speeding car traveling east away from the intersection. Okay, so if I draw this kind of intersection, right, I've got north, east, south, and west. So the policeman is traveling south towards the intersection. So the policeman's going this way, okay, from the intersection. And then what way is he seeing? The car's traveling east. So our speeding car is going this way, okay? So this is our police car. This is our speeding car, if you will. And then the distance between them is going to be, let's just call it D. Okay, I'm going to take off these letters so they don't confuse you. Okay, so first what you need to notice is that the police car is getting closer to the intersection. So my dp dt is going to be negative. Okay, so it says that, let's read it really quick. So when the policeman is 0.6 miles from the intersection, so this is 0.6, so write P equals 0.6, and the car is 0.8 miles from the intersection, and so that's S equals 0.8. The policeman's radar shows the distance between them is increasing at the rate of 20 miles per hour. Okay, so what we're going to say here is I don't really like that letter, dt, okay, is equal to 20 miles per hour. So 20 miles per hour. Okay, so we know what each of these things are. Now it says if the speed of the police car is 60 miles per hour, then what is the speed of the car? So the police is traveling 60 miles per hour, and it's going towards the intersection. So that's going to be negative 60 miles per hour. Okay, and then we know that the d is 20, so we're trying to find what is the speed of this car, S. Okay, so what do you think that we're going to do here? So we can even put right here, find ds dt. So we have an idea of what we're looking for. Okay, so I can write Pythagorean theorem is p squared plus s squared equals d squared. Okay, so if I figure this out first with our distances that we know, we've got 0.6 squared plus 0.8 squared equals d squared. Get my calculator out. .6 squared plus 0.8 squared, and we get 1, and the square root of 1 is 1. So d is 1. 1 mile. There's 1 mile between them when this all starts, okay? All right, so now I have to take the derivative to find my rate of change because I'm trying to find ds dt, which is going to be right here. So 2p dp dt plus 2s ds dt equals 2d dd dt. Okay, so now notice there's a 2, 2, and 2 in every term, so I can cross the 2 off. So it's always something that's nice to do, okay? So P I was given as 0.6 at that moment, that dp dt was negative 60. Okay, so we're plugging in each of these values. And then S was 0.8, and that's what I'm trying to find, is ds dt. And then that equals 1, and then dd dt was 20. Okay, so now we have to solve for the ds dt. So if we multiply 0.6 times negative 60, this is negative 36, equals 20. So if I add the 36 over, then we get 0.8 ds dt equals 56. So 56 divided by 0.8 is 70. So ds dt equals 70. And remember, that's 70 miles per hour, or you could write mph. Okay, so what's my sentence here? ds dt, this represents how fast the speed of that car is, right? Because of how fast they're separating in their distance. So I'm going to say the car is traveling 70 miles per hour when, okay, so we always have to say when. So we want to look here and say when, what one do we know? So you could say a couple things. You could say when he is 0.8 from the intersection and the police is 0.6, or you could say when the police car, or when he is 1 mile away from the police car. Okay, so there's a couple of things you can say there. You always want to go back to what you're given though. So when the policeman is 0.6, when the car is 0.8. So when it is 0.8 miles away from the intersection. We wouldn't really have to say what the police was at that point, because we know he's 0.8. Okay. All right, so we have one more. Gravel is falling on a conical pile at the rate of 10 feet cubed per minute. So gravel is increasing the volume of this cone, right? Okay, so at all times, the radius of the cone is twice the height. So that's going to be really important, right? So R equals 2H. Okay, so we want to keep that in mind. All right, so now it says find the rate of change of the height of the pile when the radius is 6 feet. Okay, so if the radius is 6 feet, I can solve for the height. I can also do this. So V equals 1/3 pi. And then instead, now we're trying to find the rate of change of the height of the pile. So that means I need to have dH dt in my problem, right? So instead of R right here, I'm going to write 2H in its place. So 2H squared times H. So all I did is rewrite the volume equation. Instead of having this R squared, I wrote 2H and then squared. Okay, so if I multiply that out, 2 times 2 is 4. So this is going to be 4/3 pi H cubed. So this is our beginning equation, 4/3 pi H cubed. Okay, so once I know what the volume is, when I've got it in respect to the radius with the height, then I don't have to worry about the radius anymore. Okay, so now it says the gravel is falling on the pile. So the pile is getting bigger, 10 feet cubed per minute. So that's going to be our dV dt is going to be 10 feet cubed per minute. Okay, and then it says the radius of the pile is 6 feet. So let's write R equals 6. We're going to have to say, so if R is 6, then what is H? Okay, so if R is 6, I divide by 2, and we get H is 3. So at the moment that the radius is 6 feet is the moment where how fast this is growing, okay, the height. So now I'm going to take my derivative. So the derivative of the volume is dV dt. Now I'm going to take this 3 and multiply by 4/3, so I get 4 pi H squared. Don't forget that it's changing with respect to time. Okay, so you have to have your dH dt on there. Okay, so now I know that dV dt was 10. And I know that H was 3. And dH dt is what we are solving for. Okay, so now I can solve for dH dt by dividing by all of this stuff, right? So I've got 10 divided by 4 times 9, so 36 pi equals dH dt. And think about when a height changes, that's what your units are. So if the height is changing, that is just feet, right? So this is feet per minute. Okay, so if we write a sentence, then we say the height is changing. We could also say increasing is a better word to say right there. Okay, so the height is increasing at a rate of 10 over 36 pi feet per minute when the radius is 6 feet. Okay, so that would be our sentence for that. All right, so you've had an introduction to it. Go ahead and watch this. At our Zoom meeting tomorrow, we will go through these again, follow-up questions that you have, and then we'll start a couple of your homework problems. Okay? All right, you guys, have a good night.